Today we discuss theorems on limits from section 16. First we discuss theorem 1. This is a necessary and sufficient condition for the existence of this limit. Limit z tends to 0, f of z equal to omega naught. This is if and only if limit xy tends to x0 y0 in the xy plane. U of xy, the limit of u of xy should be u0, and limit xy tends to x0 y0, v of xy is equal to v0. If these two limits exist, then you can say that this f of z tends to omega naught, where omega naught is equal to u0 plus iv0. So we need to prove this theorem by assuming these two conditions first. Okay. So we will prove that the limit f of z is equal to omega naught if these two limits exist. Okay. So what is the meaning of these two limits? First of all, we consider xy plane, and this is our x0 y0. So you consider two functions from this xy plane. This is the function u, and we have another function that is v. Okay, these are two functions. Both functions are to this real line R, and v is also the codomain of v is also R. So when you consider a path which converges to x0 y0, that means any xy converges to x0 y0 through an arbitrary path, the corresponding u of xy, that's a real number, u of xy and v of xy, u of xy will converges to this u0, and the corresponding v of xy will converge to v0. Okay, if this happens, whenever this tends to this, then you can say that this u tends to this number and this v tends to this number. Okay, so whenever this happens, or these two conditions are equal, okay, that is the meaning of these two limits. Whenever f of z tends to omega naught, then these two conditions hold, and whenever these two conditions, whenever these two limits hold, then we have f of z, limit of z equal to omega naught. Okay, so the meaning of this is these two limits, u of xy tends to u0 and v of xy tends to v0, means if you consider any epsilon disk here, then we can get or you can consider the same disk, or for a given epsilon. The meaning of this limit says that whenever we consider an epsilon neighborhood here, then there exists a neighborhood delta 1 neighborhood here. This is delta 1 neighborhood, for which image of every element of this delta 1 neighborhood should be an element of under this u. Okay, it will be an element of this, and if you consider any epsilon neighborhood here, then you can get another delta 2 neighborhood here, and image of every element of this delta 2 neighborhood under this the function v, you can get that should be an element of this epsilon neighborhood. Okay, so this is the meaning of the convergence of u of xy and v of xy. Whenever this happens, then f of z tends to omega naught. Okay, so that is the meaning of this theorem, theorem 1. This is considered to be the first theorem of limits. Okay, so what do these two statements meant for? That is u0, u minus u0 can be made less than any epsilon by 2 whenever the points xy belongs to this delta neighborhood. Okay, so whenever a point belongs to delta neighborhood means, if you consider a delta neighborhood here, if you consider delta neighborhood, then about this x0 y0, the meaning of this is for any xy belongs to this. I'll give you some large picture for this. So if you consider x0 a neighborhood at about x0 y0, if you consider any xy belongs to this, how would you say that xy belongs to this neighborhood? If the radius of this neighborhood is delta 1, then the meaning of this is xy, the distance between xy and x0 y0. Okay, this will be always less than delta 1. That is the meaning of this. Okay. Okay, so whenever the distance between x naught, y naught and xy is given by root of x minus x naught whole square plus y minus y naught whole square. So this can be made less than epsilon by 2 by assuming the first limit here. Whenever the distance between xy and x naught y naught is less than delta 1. Okay, that means 0 less than square root of x minus x naught square plus y minus y naught square is less than delta 1. Similarly, we apply the same definition for this the second limit. If we will get v minus v naught less than epsilon by 2 whenever 0 less than square root of x minus x naught square plus y minus y naught whole square is less than delta 2. Okay, so if you consider the minimum of this delta 1 and delta 2 for those values of xy which lie inside this neighborhood, that means delta neighborhood, where delta is the minimum of this delta 1 delta 2, we can assume these two conditions simultaneously. Okay, so that means if we choose the minimum of these two quantities, we will get this quantity u minus u naught less than epsilon by 2 and modulus v minus v naught less than epsilon by 2 whenever 0 less than square root of x minus x naught square plus y minus y naught whole square is less than delta, where delta is the minimum value of delta 1 and delta 2. You might have seen these ideas while you're proving the theorems in real analysis. So this is the assumption right now. Now we will prove that f of z, we are given that f is equal to u plus iv if you remove those x and y, and we will prove that this f converges to, or limit of this f is omega naught, where omega naught is equal to u naught plus I v naught. Okay, so we need to prove that the distance between u plus iv minus u naught plus iv naught, this distance between these two f and omega naught, this is less than or equal to, we know that this quantity is in fact this is equal to, by considering the modulus of this, we will get this is equal to u minus u naught plus I times v minus v naught. Okay, modulus of this is this can be made less than or equal to u minus u naught, modulus of this plus modulus of I times, modulus of I is equal to 1, so modulus of I is 1, then modulus of v minus v naught. Okay, so we know that this quantity is less than, we know that this is less than epsilon whenever 0 less than mod x minus, because this is less than epsilon whenever when you write this is epsilon by 2 plus epsilon by 2, that is equal to epsilon whenever this happens. Okay, so what is the meaning of this condition, x minus x naught whole square root of x minus x naught whole square plus y minus y naught whole square less than delta. Okay, but we know that this is the modulus of 0 less than, this is the modulus of x plus iy minus x naught plus iy naught. Once you try to find out the modulus of these two, difference of these two complex numbers, you will get this complex number is in fact x minus x naught plus I times y minus y naught. Then the modulus of that quantity will be this one. Okay, then we can say that this can be made less than epsilon whenever this is less than delta. Okay, which proves one part. Okay, when you assume these two conditions, we can easily prove that f converges to this u naught plus iv naught. That means the meaning of this statement is modulus of f of z minus this is our omega naught. This can be made less than epsilon whenever this happens. What is the meaning of this? This says that modulus of Z minus this is our Z naught less than delta. Okay, so this proves one part. Okay, now we prove the converse part by assuming f converges to that omega naught. For the converse part, we assume a limit f z times z naught f of z equal to omega naught. That is to assume modulus of f of z minus omega naught is less than epsilon whenever this mod z minus z naught less than delta. So if you translate this to xy term, we can say that modulus of u minus this v naught or u plus iv. So we can put it as u plus iv minus this is in fact f of z minus omega naught is u naught plus iv naught. So this difference modulus of this difference is less than epsilon whenever what is the meaning of this? Whenever square root of x plus z minus z naught is in fact x minus x naught plus I times y minus y naught. So this is square plus y minus y naught square is less than delta. Okay, 0 plus. So this is in fact we need not consider the point z naught for considering the limit. Now we consider these things. Okay. So we need to prove that we write here what is the requirement. We need to prove two distinct limits, that is one using u of xy tends to u naught, u of xy tends to u naught, and we need to prove that v of xy tends to v naught as well. We need to prove these two things. Okay, so we start with those moduli u minus u naught. First of all, we consider this, and next we will consider v minus v naught. We know that this modulus of this u minus u naught is always less than or equal to modulus of u minus u naught plus I times v minus v naught, because the modulus of this complex number is square root of u minus u naught whole square plus v minus v naught whole square. So that those quantities always greater than or equal to this thing. Okay, or you can take the modulus of real part is always less than the modulus of the complex number. Okay, so for this inequality you can refer this result that you have discussed in your plus 2 classes. If z equal to x plus iy, then we can say that mod x is always less than or equal to root of x square plus y square, which will be the mod z. Okay. That is the real part is modulus of real part is always less than mod z, less than or equal to mod z. Similarly, you can get the imaginary part as well. Imaginary z is always less than or equal to mod z. So if you use this thing, you can say that modulus of u minus u naught, that is the real part of this complex number, is always less than or equal to modulus of this complex number. Okay, but this is in fact modulus of u plus iv minus u naught plus iv naught. Okay, so this is same as this one. Similarly, the similar fashion you can write this always less than or equal to v minus v naught plus I times this is again u minus u naught. The imaginary part is always less than or equal to, so we can use the same reference. So we write the same thing here, u minus u naught plus I times v minus v naught. Okay, because this v. This is because this is the imaginary part of this complex number. Okay, so similarly this is same as u plus iv minus u naught plus I v naught. Okay, so but we know that our assumption is this f of z tends to omega naught. So this is always less than epsilon. Okay, so this can be made less than any pre-assigned positive quantity. So if this is less than epsilon, corresponding to this epsilon there is a delta, then corresponding to any positive quantity epsilon by 2 there should be a delta. Okay, so we can write this quantity is less than epsilon by 2, or we can write epsilon itself. Okay. So So this is less than epsilon whenever this is less than delta. So we can say that from the first result we can get this quantity is less than epsilon whenever this happens. The similar fashion you can write this is less than epsilon whenever this happens. Okay, that is modulus u minus u naught less than epsilon whenever 0 less than square root of x minus x naught whole square plus y minus y naught whole square is less than delta. Similarly, you can write the same thing in v, modulus of v minus v naught less than epsilon whenever 0 less than square root of x minus x naught square plus y minus y naught square is less than delta. Okay, so this proves the converse part as well. So this is theorem 1. Next we will discuss theorem 2.